Hello everyone. Have you ever watched a rocket shoot into the sky or noticed how a gun kicks back when fired? At first glance, it feels mysterious. But in reality, it's one of the most beautiful outcomes of Newton's laws, the law of conservation of momentum. Newton's second law explained how force changes momentum, while his third law showed that forces always come in equal and opposite pairs. Together, they give us a powerful conclusion: in an isolated system where no external force acts, the total momentum always remains constant. Let's take a classic example. When a bullet is fired from a gun, the gun pushes the bullet forward. At the same instant, the bullet pushes the gun backward with equal force. Since these two forces act for the same time interval, the bullet gains forward momentum, while the gun gains backward momentum of the same size. So, the momentum lost by the gun equals the momentum gained by the bullet. As a result, the total momentum of the bullet gun system stays the same as it was before firing, which is zero. This brings us to the law itself. In an isolated system, with no external force, the total momentum of the system remains constant. In simple terms, even though individual objects may speed up, slow down, or change direction, the overall momentum of the system stays the same. Let's derive it step by step. From Newton's second law, force equals change in momentum divided by time. From Newton's third law, the force on body A by body B is equal and opposite to the force on body B by body A. This means that the change in momentum of body A is equal and opposite to the change in momentum of body B. When we add them, the total change in momentum of the system becomes zero. That's why we conclude the total momentum before interaction is equal to the total momentum after interaction. This law is everywhere around us. In rockets, gases are expelled backward and the rocket moves upward. In gun recoil, the bullet moves forward and the gun moves backward. In collisions, cars exchange momentum, but the total momentum remains unchanged. In explosions, fragments fly in all directions, yet the total momentum of the system stays the same.
Let's solve one. A gun has a mass of 5 kilograms. It fires a bullet of mass 0.05 kilograms with a speed of 200 meters per second. What is the recoil velocity of the gun? Step 1. Before firing, total momentum is 0. Step 2. After firing, the momentum of the bullet plus the momentum of the gun must still equal 0. So let's write it in words. Mass of the bullet multiplied by its velocity plus mass of the gun multiplied by its recoil velocity equals 0. Now substitute the values. Mass of the bullet is 0.05. Multiplied by 200, we get 10. Then add 5 times v, which is the recoil velocity. That equals 0. So the equation is 10 plus 5v equals 0. Solving for v, we get v equals -2. That means the gun recoils backward with a speed of 2 meters per second. Let's recap what we've learned. The law of conservation of momentum states that the total momentum of an isolated system always stays the same, even if individual objects within it change their motion. This principle comes directly from Newton's second and third laws. It explains rockets, gun recoil, car collisions, and even explosions. So to sum up, momentum is never destroyed, it is only transferred. I hope you now see how momentum connects Newton's laws to so many events in our daily life, from firing a bullet to launching a rocket. See you in the next session with another fascinating concept of physics.